So a couple quick announcements. First off, Canvas grades for everything else for midterm 2 should be up. Your ones on Canvas right now should include your group grade. Just like last time, if you're part of a group and you can't see the rest of your grade because we can only sort of return it to whoever the lead person is, if you'd like to see your other one, please email me. I'm happy to share that point out. Overall, midterm average was 69.2, not too bad. There is one more update I need to make. Somebody made a very, very astute observation. One of the questions I designated it as, which of these is an aldol donor? Aldol specifically. One of the compounds, you can make an enolate, you cannot make an aldol with it. It's just di-substituted enolate, and as a result of that, should not add. So I'm going to accept both answers, yes and no to that one. So your grade will likely go up by one more point as that point. So I have to make that update, and I'll do the re-upload with Canvas after that. So today, we'll go through the final voting at the end of class. One more quick announcement. We will have no in-person lecture on Monday. I chose last class to pull down the pace a bit so we could spend a bit more time. We're going to go through the demonstrations of that of synthesis through today. But it will mean that I will have other wrap-up material that I will do as a video lecture that you guys can watch at your leisure. Probably get it posted through Monday or Tuesday. So last class. We are now using electrophilic aromatic substitution to do multiple different steps. This is where we've not just got the rules for how we do group additions, but it's now saying that depending on the group we add, we change the personality of the benzene. Benzene on its own is our sort of our root case, but depending on what's on the benzene, the next group that gets added can change both its reactivity, that's what we call our activating and deactivating, but also the position. We have ortho, para, and meta. So we have these kind of a grid of what kind of reaction could happen. This gets us to polysubstituted aromatics where we have more than one substitution. So review question. If I gave you these conditions, what is the product? So take a moment and discuss. How do you think you would form a product here? What do you think your product is, major, minor, or otherwise? Okay. So, type of reaction, this is our Friedel-Crafts alkylation. You can tell that from our acid catalyst, in this case a Lewis acid. Our starting material is a simple alkyl halide. So this falls in that category where we're making a carbocation, right? That's our electrophilic species, and we're going to add through to this. So the intermediate we're going to make after the aluminum trichloride addition is going to be my benzene ring. It's attached to a 1, 2, 3, 4 carbon chain. So carbon 1, 2, 3, and 4 is carbon 1, 2, 3, and 4. On carbon 4, immediately, will be a carbocation. Okay, that's one possible intermediate. And let's deal with this. If this is what formed, what would my product be? So I'm probably going to use one of these two centers. Geographically, they're close by. I've got both my nucleophile, this is my aromatic ring, and my electrophile, the carbocation, in the same molecule. If you imagined some sort of attack like that, this would give me a 4, 5, 6 membered ring as a product. So I could get that. We're highlighting specifically this is our new bond, where this would be 1, 2, 3, 4, 5, and 6, which if we go back to our numbering, let's do this as 1, 2, 3, 4, 5, and carbon 6, where we're using carbon 6 as our nucleophile. We've done this ring closing. 6-membered ring. Possible? Not possible? What is your guys' opinion about that as a potential suggestion? Yeah?
You're generating a carbocation. It's going to want to move.
You're going to make your carbocation want to move. Possible. This is legal, right? Ring size is okay. Major? Maybe not. So what's the other, again, so what we've done is we made an intermediate that's valid. We can do a ring closer off that. That's a possible one. So we're going to put this on the deck. This is one of your two possible products that you could make. Expected both of the other component. It can move. Where is it going to move? Yeah, if this were to do a migration, right, a proton migration, I can move my terminal carbocation to potentially this position here. Numbering it off again, 1, 2, 3, 4, and 5, where this is again carbon 6. Nucleophile's in the same position, but we've slid the carbocation into an internal position. That gives me a secondary carbocation. Now if I do a ring closure there, I'm going to renumber this with a different color. That's 1, 2, 3, 4, and 5. This is a 5-membered ring now. Still allowed? It's not too small yet. So that will give me my benzene, and now I'm appending a 5-membered ring onto it. And on carbon number 4, the point of attachment, this bond right here, where if I'm numbering those off, that's 1, 2, 3, 4, and then 5 for my ring cycle. On this carbon, we still have this appended methyl. There will be a methyl that's now sticking out of the ring. That's possible number 2. Now you can debate this. As it works out, which do you guys think is major, which is minor? So guy in the top, major, guy in the bottom, major. Top or bottom? Bottom because more stable carbocation. Turns out in this case here, it actually is a little closer than you think. If you run this reaction, the observation is, again, both, top is maybe a little bit more of a major product. Only in this case. Now what might, again, with that new information, what can you conclude about the rate of closure compared to the rate of isomerization? What is faster? If I'm telling you this product here, if I gave you the new information that this product here is your major product, what can you conclude about rate here, K1, versus rate here, K2? Ring closure versus isomerization. If that's major, which one must be faster? Ring closure. And that's only because the carbocation cannot get away from your nucleophile. This is an advantage you can use as long as you are intramolecular. Any other time, if I form a carbocation and it has to go and find a benzene, rearrangement's going to win. This is the one case where you can potentially allow a primary to form and ring closure to win only because they're on the same molecule. And this kind of follows what we've seen with things like hemiacetals or hemiketals, things like that. That ring bond formation allows an intramolecular reaction which can outcompete what would normally be unreliable stabilities. Okay. So today, we're going to dive into synthesis strategies. Let's use these principles to build up complex molecules. And we're going to introduce the concepts of different orders of reactivity and how we deal with other competing nucleophiles, things like phenols and anilines. So this is your table. This is the most important one for sort of allowing and rank as we go through the material. Remember, take your benzene as your center point. That is your unactivated, deactivated. It is your reference point. If we add electron donating groups to it on this side, we increase the activation. They are more nucleophilic. They go faster. And as a result of that, these become orthopara donors. On the other side, the more deactivating we add or the more electron density we pull out of it, they slow down the reaction and they also become meta-directors. Halogens are the weird crossover where they are both deactivating, they are slower than benzene, but they yet are still orthopara directors. And this is that tipping point where sigma withdrawing and pi donating is starting to have a fight. But that's your basic piece. So if I was going to make this molecule from benzene, that means I'm doing 2 substitutions. I need to add 2 different groups. How would you do it? What are the 2 reactions you think you need to build this? Forget about position for a moment. What are the 2 electrophiles I need? Yeah, I need nitration. So this here is going to come from some NO2 plus, right? What about the top? What is that? Yeah, this comes from my carbonyl positive. That's Friedel-Crafts acylation and nitration, right? Those are the 2 pieces here. Okay, good. That's step 1. Now we have a problem of order of addition or position. What I mean is, let's say we start from benzene. Pick, which one do you want to use first? Nitration or acylation? And again, at this point, you can just pick. Thank you. If you just pick acylation first, my conditions will be something like my acyl chloride and aluminum trichloride, right? If I have those 2 conditions, my product is going to be acyl. Cool. What did I just do to my ring? Is it activated or is it deactivated relative to benzene? It's deactivated because I added an electron withdrawing group? Yes, cool. So that means the next step is going to get harder. So keep that in mind. The first thing you did, yeah, it's added a group, but it's changed the personality of your molecule, and that can hurt you depending on which type of reactions you're using. But yes, it means your next step is going to be a little harder, and you're going to have a very powerful or more powerful electrophile than you normally would have needed. That's one option. Okay, if I did the opposite, let's say I nitrate this first. That's HNO3, sulfuric acid. That would give me my nitro product. Again, did I activate or deactivate the ring by putting a nitro on there? Did I activate or deactivate it more than acyl? Which one of these is worse? Yeah, nitration is way down here, acylation is here. So again, both are fine. You can do both of these. Remember the thing in your mind, keep your consequence. I've deactivated the ring for both, which means the next step in both cases will be harder. Nitro is a big step harder. I have really deactivated the ring, which means I'm going to have to climb a bigger hill to get that to react the next time. That may influence your decisions about order of addition, right? You're setting yourself up for potentially a harder pull to get out of this hole. All right, what do we do next? If I'm at my acyl, the red guy up top here, I'm at this one, I need to now nitrate it, right? So I'll use the same conditions, HNO3, H2SO4. That'll get me to my nitrated product. Question, where does the nitro go? Meta to what? To the acyl, right? This is where meta direction matters because benzene has no position, has no point of reference. It's a circle. The second that I have this in place, this group is saying I am deactivating and I will preferentially add something to the meta positions of my product. Those are the reactive centers I'm going to choose. Why? Because if I was to hit the ortho or para position, the cation I'm making will be destabilized relative to my methyl one, right? So that means I'm totally legit. Oops. It's totally fine if I were to add a nitro here, right? I'm adding a nitro to the meta position because the group that was already on there by the path I'm choosing selects for that position. Legit, works. What if, hypothetically, what if I came from here, this way? Conditions will be the same, right? It's just Friedel-Crafts acylation here. Aluminum trichloride. What's the group here? Nitro, it's deactivating. Where will it add the next group? Ortho, meta, or para? Nitro is what directing? Meta again. So it's going to try to add meta to the nitro, which in this case doesn't hurt me. It has the same selectivity. They are both meta directing and they are meta to each other. So it doesn't matter which one you put in first. The selectivity criteria say that both of these pathways are equivalent. Reactivity, there might be a slight preference for deactivate it a little bit first and then go in for the kill with the bigger deactivator. If you chose the other pathway, you're setting yourself up for a strongly deactivated group that you are then asking, please, please, please do one more reaction. It's like, oh, dude, I've already got a nitro. Just leave me alone. That's a consequence of the relative reactivities you have, and it comes down to the strength of your electrophile. It turns out nitro is a phenomenal electrophile and can work regardless of how deactivated the group is. Yeah?
Does deactivating it more give you a better fraction of the meta product?
A little bit, yes, you're right. So the more deactivating will also give you higher meta selectivity, but you have to balance that against, I would love to turn graphite into diamond, but that is a very hard road. So my boss used to say 20% yield of 0% product is still 0, right? Like it doesn't help you. But you're right, there's a higher selectivity on this too, true. But in terms of synthesis, one thing you will start to see is there's not just, okay, selectivity is one rule, but relative reactivity governs what is possible. All right, that's those two. Okay, let's do this. How do you get from toluene over to that guy? And why we're doing this too is there's two pieces. The thing I want to remind you here is there's what you're going to add, but remember the groups that you add do not have to stay as the groups you see. We have reactions to modify these groups, not just the ones we've added. We've only talked about sulfation, nitration, halogenation, and Friedel-Crafts, right? What do I do to put an NH2 on the ring? It's not one of those four. I can't do it directly. How do I get an NH2 on the ring? Think way back. This is like 3 classes ago now. I'm not going to just add, there's no way to just add NH2 plus. That doesn't exist. What do I use instead to stick a nitrogen on a ring? I can use nitration, right? Nitration gives me a carbon-nitrogen bond, and then I have to reduce the nitro to an amine. So I can use the nitration to introduce the atom, and then I have to modify the nitrogen by a reduction. That's one. Second is, that's a methyl. That's not a methyl anymore. How do I transform a benzylic methyl into something like a carboxylic acid? What's the reaction I need? Yeah, it's oxidation, right? I can take a benzylic center, and I can oxidize it to a carboxylic acid, right? So now we have a couple options. In general, the order is going to be what we have to figure out. But if you think of the catalog of reactions we have to do, one, I need to turn a methyl into a carboxylic acid, right? That's something that has to happen somewhere. Two, I need to take a CH bond on my ring and turn it into probably a nitro. I need to introduce a nitro somewhere. Three, I'm going to probably take my nitro and turn it into an NH2. It's a reduction reaction I'm going to need to do. So obviously, I'm going to have to put the nitro on and then reduce it. 2 and then 3 has to be the sequence. And 4, what's the substitution pattern I'm aiming for? Meta. I need to get a meta selection. So this is where the order matters. How we do what will help influence here. What would happen if I decide to just nitrate first? What's the directing group here? Yeah, this is ortho selection. So I could nitrate first. There's nothing wrong with that. It's probably going to go in the wrong position. This will go ortho-para, not meta. Because the methyl group is what? Methyl is it's mildly activating, it's ortho-para directing. How do I turn a methyl into not a methyl? What do I need to do? Yeah, if I oxidize this first, if I turn my methyl, and I did this first step here, right there, if I were to oxidize my methyl group into a carboxylic acid, it is now a deactivating group. It is now meta-selecting. So I would probably turn my methyl into this. This is something like Jones. Remember, benzylic groups, benzylic CHs, can be oxidized all the way up. So I can turn my methyl into my carboxylic acid. Now there's a carboxylic acid, it is deactivating. If I have a carboxylic acid, my next step is going to be nitration. That's going to be this guy right here. If I have a deactivating group, my nitro, after that step, compound B, so compound A, I'm going to say is my carboxylic acid. Compound B, if I put my carboxylic acid in, now I can direct potentially here, NO2, and here, OH. So I can nitrate, it'll go meta like I want, it deactivates the ring, still allowed. Nitro is a powerful deactivator, but it can be put on a deactivated ring slightly. Yes? Remember, benzylic oxidation is possible. If you have a benzylic CH, Jones does a radical oxidation at that center to turn things like alpha carbons and alpha CH2s all the way up to carboxylic acids. 2 lectures ago, we were giving our the decoration that we can do around a benzene ring. So that's in the same one as we did phenolics. Yep. So then we come in with number 3. Now we'll do the reduction. This would be something like palladium with hydrogen, right? That's a reduction step. And this is one of those ones that palladium on hydrogen, we can hit something like nitro down to amine. If we push it really hard, we will also chew up something like the carboxylic acid, but that is why we use, remember, what is the reagent we usually use to kill a carboxylic acid? Back to something like a methyl. Not a base. If I'm trying to reduce a carboxylic acid, you have one reagent that you will reach to that ends all carbonyls' lives. What is it? No, SOCl acid chloride, lithium aluminum hydride. That's your massive power reset for any carbonyl. Hydrogen on palladium will hit selectively my nitro down to my amine. I can do that reaction without touching my carboxylic acid. Okay? So this is a strategy where we're not just saying which groups do we put in, but remember, the groups you have around the ring can be secondarily functionalized. You can now mix and match between reactions that we've used before plus the actual insertion. And the order is the thing that helps. All right, what if we wanted to do this one? This is a pretty much same idea, slightly different order, slightly different position. So once again, if we did the things we have to do, we still are going to do something like I have to insert, my CH has to become a nitro, and then 2, my nitro is going to become an amine, NH2. 3, I have to take a methyl group into a carboxylic acid again. And 4, what's my selectivity now? Orthometa-para? This is para selection. So what changes? Same kind of stuff, different positions. How do I do this now? What do I do first? Yeah, if you use the methyl group as your director, if I choose to do this one first, now I'm going to make, at compound C here, this is going to be my methyl aromatic ring and nitro. Asterisk, so let me redraw that. Here is going to be methyl, benzene, nitro. Is that the only compound you're going to make? What else are you going to make? Right. Do you know which one major, minor? If you had to guess. Yeah, ortho's probably a little bit. Remember, the 2 things we've got to help us, para is favored by sterics, right? It's the one that's remote. It's away from the methyl group. Para's help there. Ortho is favored because of probability. You got 2 of them, so there's a little better. In this sort of case, you probably end up with a pretty close 1-to-1. This is totally acceptable. You have no other way to only hit para. So this case, you would make both, and that means you're going to have to separate. You need to do something like column chromatography, distillation. There's no way to get this better, and that is fully legit for synthesis. That is all you can do. You will make both, and then you're saying, I need the para because that's the one I need to go, so I will separate or purify them there. And if you guys are really interested in this, 3rd, 4th year, we start telling about things like selective crystallization, selective distillation. Lots of cool ways to get at this point. But there's no way chemically to deal with this. This is a post-reaction point. All right, after separation, we've got our para. Then what do we have to do here? Nitro still needs to be reduced, and one needs to be oxidized. Do you care which order you do that in? Yeah, nitro is going to be hydrogenated, right? Just like last time. The methyl group is going to be oxidized using Jones. You can choose any direction, right? It doesn't really matter, those two options, because those two don't really interfere with each other too heavily. Personally, if it was me, because I know the steps work out okay here, I would probably do Jones first in order to turn this into my carboxylic acid nitro compound, NO2, and then I do my H2 palladium, hydrogenation, my nitro becomes my amine. But you could choose either of those two. They are not mutually exclusive. They can kind of both work, right? No issues on that. Does that make sense? The concept you're dealing with here is you've only got 4 ways of sticking things on the group, and from those 4 things that you've got, acylation, alkylation, you can also further react. That's also, remember, I can delete carbonyls using Wolff-Kishner or something like Clemenson. I can oxidize benzylic centers using like Jones, chromium reagents. I can reduce nitro compounds. So you can post-functionalize all the reactions using what we've done throughout this course. So in general, if you've already got one, we've talked about what happens if the next thing comes in. Single monosubstitution to disubstitution follows the rules we talked about at the beginning. The next level of complexity is, what if you have already 2? Where does the third go in? And this is something where those groups can actually reinforce each other, or they can actually basically be antagonistic to each other. What I mean is, imagine you had this first example. If this guy here was a very, very strong meta-director, and this guy here is a very, very strong meta-director. Okay? So let's take it individually. Blue guy, whatever that happens to be, if that is a meta-director, just look at it on its own. You can say, this meta-director wants to put a group here or here. Right? You take it individually and you say that top one wants a new substitution. The next one, if it existed on its own, would be meta to that group. Okay, the green one, also a meta-director, wants to put one where? Here and here. So what do you think the product would be if I have 2 meta-directors on here? I've got green circle, blue circle, and green-blue circle. Which wins? Everything is pushing to the same point. They are reinforcing each other's selectivity, and as a result of that, you've only got one chance it can go, right? Not only are there other, G is already in one position, Y is on the other position, but both of them are pushing to one particular outcome. What about this? Now remember, if they're meta-directors, are they activators or deactivators? So is this going to be a hard reaction? Probably, but what we can do this, probably not alkylation, we could do nitration, sulfation, maybe halogenation, but we can at least say the good side is it's going to select for that position exclusively. Everybody's pushing the same way. All right, what if, let's take the second one, do a different one. If this one was, let's say, meta-directing, and this one was ortho-para-directing, let's do the same analysis. This is meta-directing by pink, which puts it there or there. Green, ortho-para, says, I want to go here, whoops, here, here, or here. Okay. So where does the group go if that's your distribution? What's your pattern say? Green, green, or pink, green? Again, it's reinforcing. So we got 2 options. So by gut, what do you think? Pink, green, number 1, pink, green, number 2. Which wins? Because? Probably, yeah. Totally legit. Sterics would probably help you out quite a bit here. But that's it. The multiplication of different groups follows this pattern. You have to go through this option of looking at what's there, and generally, by synthesis, these are the kind of situations you're trying to gear yourself towards. If you can set yourself up for both groups pushing to common places, you've got a lot of control. This is good. Let's do this last one. What if this one was meta-directing and this one was meta-directing? Okay. Top green says I'm going to be meta to green. Bottom is going to be meta to blue. Now what? You get what is officially known as a mess. This is going to be a lot harder. You've got two different groups which have orthogonal selectivity. Green is saying meta to me, the other one's saying meta to me. There's no good overlap. It's going to come down to power at that point, sterics or something else. So you're going to have to go to something else. If this one happened to be a nitro, so it is a strong meta-director, versus this one was sort of more like a carbonyl, which is kind of a weak meta-director, nitro is probably going to win the day. That's where you go back to your ranking system. The more powerful director is the one that's probably going to give you a major. But if possible, you stay away from these options. This is really, really hard to do because you're going to end up with messes. No, nothing else in that point. Okay, let's go through these examples. I've got on the top 3 groups. Look at the conditions, H2SO4, what's the reaction I'm doing? If my conditions are just H2SO4, this is what? Alkylation, nitration, sulfation, halogenation. This is sulfation. H2SO4 makes my SO3 under acidic conditions, right? This is, I'm adding effectively SO3H+, right? Okay, that's the group. Where does it go? Let's do the decomposition. So you take them one by one. Oxygen phenol is what kind of director? Orthopara or meta? Let's go back to the table. Oxygen is what? OH? What is it probably closest to here? Yeah, it's sort of like this, right? It's not this far. It's not negative. We're not dealing with anionic, right? This is very acidic conditions, so you have protonated phenol. It's probably closest to this. So yeah, it's an activator. So it's going to be orthopara. I'm going to say here, here, or here. All right. Methyl is what kind of director? Methyl is a orthopara, mild activator. So again, here, here, and here. Nitro is what? Right. It is going to give you here. So nitro is here and here. All right. What wins? Again, open class. This is an open discussion. What do you think? This is a case where you've got a lot of competing factors. What's going to win? So I'm picking up on conversation. Is this where people think? Yes? Why? You're right. This wins. Why does this win?
Two major factors. One is the sterics, and then the meta position to nitro essentially wins out.
Yeah, exactly. Nitro is a big heavy hitter. That's number one. It has a big, strong impact because if you look at your overall table, it is decidedly at one end of it. That's one. Yep. 2, that position that we've highlighted is the only one with at least 2 factors pointing to the same center, right? Methyl might be mild, but you've got a mild plus a strong versus just kind of in between. You can say that 2 beats 1. That's one part 2. Absolutely. Sterics, yeah, I guess there's a bit of that part too. You know, there's a bit of maybe steric occlusion here. I'd say a big one though is going into nitro and saying, I know you're a meta director, but I don't care. That is a big statement, right? That is a massive thing that you think that you're doing. Because remember, you could draw, the way to actually run this part through, to run it to ground, draw the sigma complex you think you're going to make. In other words, substitute one of these positions and make the corresponding sigma complex, and look at where the positive charge sits. Putting a positive charge immediately next to the nitro would be the consequence of hitting the center I've just focused here. If I focus here, I will put a positive charge right next to that, which is a terrible thing to do. So in the end, the directing effects can also be looked at. The resonance isomers of your carbocation that you're making will also help you. But absolutely, that's your guy. Another way to look at it too, just for this one, phenols is kind of like an enol. Go all the way back to enols and stuff. If this is an enol, you would normally say, well, the alpha center of my enol is my nucleophilic center. So there's another way to look at this, is maybe you just treat it like a carbonyl type chemistry. All right, let's do the one on the bottom. So once again, look at your groups. Look at the pieces in this group. You guys rationalize it out. Where does this go? I'm going to start here. Is that a donor, acceptor, metapara, blah, blah, blah? This guy here, this ester attached via the oxygen. What do you think? Yeah, it is effectively, it's on the oxygen side of the group. It's an orthopara mild dude. Well, no. This methyl is what? Methyl is a orthopara, right? There, and there. What about the last one? This is not, it's a carbonyl at that center. It's a metadirector here and here. What wins? So first of all, what am I adding? What is this class of reaction? My electrophile here is halogenation. I'm adding a chlorine, right? What would you guys say if I did this? Yeah, I'm just seeing if you're awake. How about that? Feel good? Yeah, that's probably right. Because, once again, the confluence, both things, you've got one center where two things are at least helping out. Yes, there's activation, other pieces, but at least that's one case where you have both trends pushing in the same direction. There's help involved in that one. Now, again, you get surprised. When you actually run these reactions empirically, you'll find some weird behaviors. And in fact, we've mentioned this a couple times. Hammett parameters, linear free energy relationships, there's so many fundamentals of how organic chemistry reactivity works, which actually comes from running these reactions and observing outcomes. So the thing we're teaching you now about predictive behavior, don't take this now like we're teaching you how to do it, but don't feel bad if it feels weird. We ran these reactions, we measured the outcomes, and then we formed the rules. So you guys are learning the basics right now, but there are cases, there's certain substrates and certain electrophiles where it actually will completely go opposite what we expect, and those are the cases we dig into because there's something special happening there. If it breaks the rule, there's something going on. Okay, these are some other ones that I will give you guys for later. We'll cover those in the video. So as we've discussed before, if I had a case like this and I had to sort of do a decomposition, I've got a donor, orthopara, right? And this guy, also a donor, orthopara. But the outcome happens to be major, minor, not observed. What's going on here? So in this case, both groups are equally pushing. We can't, by number, say which ones are sort of focusing to the same centers. All three possible functionalizations for my nitro are at least equally weighted here. Why does that become your major and this is your minor? Sterics. I'm bulky. I'm going to cause a problem. This gets harder, right? So this is at least not good. This is at least the best that you can. This is the worst of both. This is kind of like a gauche interaction, right? If you have 3 possibilities and there's nothing else to drive it, sterics can really help you out. Again, the first two, staying away from the isopropyl, makes sense. That's the least encumbered space. Next to the isopropyl, still possible, 1 out of 2. In between the two, nearly impossible. Don't do this. So, how might I make this? I'll leave that with you guys. If that's really what I needed, how do I get that? Reason I ask is we're actually kind of doing this for a ligand right now, so asking for a friend. Anyway, this is where the order of reactivity matters. The power of your electrophile will help select which reactions you're allowed to do. And this just comes down to the relative energy levels. In general, nitration is the boss. It is the final boss. You can nitrate almost anything you want. So remember, fun explosive trinitrotoluene, right? Trinitrotoluene means 3 nitro groups were added to toluene in this position. Methyl, and then we have nitro, 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 NO2, excuse me. So notice that the nitros are all meta to each other. They're orthopara to the methyl. This follows all the rules that we applied, right? And the way you make it is by taking toluene and you hit it once, you hit it twice, you hit it 3 times. Nitro can still nitro a dinitrated material. That's how powerful it gets. It's hard, you're going to take longer time, but it's doable. Sulfonation pretty much works, again, like nitro. This is a very powerful electrophile. You are allowed to sulfonate even the most deactivated sort of systems, pretty much. Halogenation usually will hit both. It gets a little bit tricky. Mainly the thing to remember is sterics can help you. Para is sometimes favored for halogenation over ortho, mainly because of steric effects. That can help out. But it is possible to add multiple halogens to a group, just like adding multiple nitros to a group. Friedel-Crafts is the one kind of diva of the system. It wants to be the first on deck, and after that, you can't play. If you have a nitrated group, you're not adding a carbon. Friedel-Crafts, both alkylation and acylation, do not work on deactivating groups. Moderately and strongly deactivating kills your ability to do Friedel-Crafts. So it just means if you want carbon, you better put it in first and then start decorating the ring. And that can sometimes go opposite with the relative directing groups that we're pushing through. So you have to use activating groups in order to get your carbons in. One thing to remember though, phenols and anilines, they have to be acylated first. What I mean for that is this. Look at your conditions. We're taking a aniline. We are doing Friedel-Crafts alkylation, right? We're taking this group, and effectively it's like methyl cation here with aluminum trichloride. Why doesn't this work? This will not produce a product. Why? Yeah, somebody give me a theory. What do you think? What did we say? If I take this group and I tried to nitrate it, I use H, NO3, and sulfuric acid. What happens? This is, I'm trying to do nitration on this ring. Yeah?
Will the sulfuric acid just protonate the amine group there instead of anything?
This is kind of like trying to do amidation on carboxylic acids. Acid-base will always win. It's the fastest kind of reactions we have. So if I tried to take an aniline and I just treat it under acidic conditions, Bronsted acidic, it just protonates. It makes it cationic, totally deactivates the ring. What's happening here? This is not Bronsted acidity. This is Lewis acidity. But same thing. I can take my aniline, NH2, I can concoordinate it to aluminum trichloride. It effectively is plus minus, and you're done. That's one problem. Second, too, is if I took a molecule like this and I managed somehow to make methyl plus, nitrogen is a phenomenal nucleophile. So you might just put methyl groups on your nitrogen, not on your ring, right? Because then I don't even have to break aromaticity. I'm just using the lone pairs of my nitrogen to alkylate. If I took methyl chloride like that and aniline, it's like, cool, SN2 all the way. There's nothing special here. So you can't take these highly activating groups like aniline or phenol. If you do anything to them that has other electrophiles around, the oxygen, the nitrogen is going to start to compete. This is where what we have to do is block them. Don't use aniline, put acyl on there. This is where we use our nucleophilic acyl substitution. If I take an acid chloride and I activate this, it's not a nitrogen anymore, it's not an aniline, it is now an amide, right? Amides are not nearly as basic anymore. You're delocalizing that lone pair. They're partially tied up into the carbonyl. But that group is still mildly activating. As long as the nitrogen here still has a lone pair, there's still some donation back in the pi system. So it's not the worst thing in the world. It's not as good as if I keep it as an aniline, but this is my compromise. Still mildly activating, now it's protected, it's not nearly as basic anymore, so now I can do my alkylation. I can hit my para position, and then what I have to do is hydrolysis. I can cut my amide back off. So now we're taking our normal earlier chapters. This is nucleophilic acyl substitution, and this is my hydrolysis step. So this is kind of like what? If I took a carbonyl, and I don't want to be a carbonyl, and I use a diol, I can turn it into a ketal or an acetal. This is modification of a functional group to erase or otherwise hide its native reactivity. It's a protecting group strategy, right? So we have the addition and subtraction where the normal Friedel-Crafts just happens in the middle. So the good news is it works. The bad news is you have to add 2 steps to both points. But this order of addition allows you to control the overall reactivity. So how do you do this now? You're going to start with benzene. You're going to make that. What are you going to do? Okay. What is the inventory of reactions I need to accomplish with this? Just like we did at the very beginning, I need to alkylate, right? I need to alkylate. I'm going to put this bond in over here, right? That's 1. 2, I need to put in a nitrogen. It's like effectively NH+, but it's not going to be NH+. That's probably actually going to be nitro followed by reduction, right? It's going to be 2 steps where I'm going to nitrate and then reduce to get my amine. That's true. What about my selectivity? Ortho, meta, para? Meta. Okay, those are your 3 things you have to do. And there are problems galore. Look at your 2 groups. Why is meta a problem if you just look at the materials you have? Yeah, alkylation is actually pushing to orthopara. If it was an aniline, you're pushing for para. That's the wrong selectivity at all, right? Okay, maybe I'll nitrate it first. But if you nitrate it, can I do my carbon? No, order of addition kills me. So I got my meta selection, but I can't alkylate anymore. Worse, could I do that by Friedel-Crafts alkylation? What would happen if I tried this? No! So we're not going to talk about this. You guys think about it, and we'll come back to it. This is a problem that you run into, and you got to get very creative. This is surgical chess with your molecule. I will do this one after. No, we got one more, You're not done yet, Hold on one second. We're not going to cover this. The thing I do want to cover is, much more important, this. So, you guys did awesome, and I'm just updating the votes from Group A. Possibly unsurprising, the Grignardians of the Galaxies win. And from Group B, it is, by a narrow margin, late stage winner, the Alpha Wolf Kishners. So if you won, please come up because I have a diabetic quantity of eggs. Okay, we're going to go through a couple of these follow-ups. So for this one, we're doing a chlorination reaction, so we're effectively going to be adding Cl+. And if you do the decomposition like we described in class, this is where we can rank or sort of work out positions. So in the top one, we've got a mild activator, so that's going to select for orthopara. And the bottom, we're going to have, this is a pi deactivator, right? It's a withdrawing group, so it's going to be meta-selective relative to that group. As a result of that, you actually have two centers which are doubly activated, and you're going to get a distribution across both. So the two possible products you could make here would be, let's say, this position here, chlorinating with your CN and your amide, and your second position here, over here, chlorination, your amide, and your nitrile. Now, of the two, you might select this one here is probably going to be your major, just because of, again, sterics. Putting this one close to the other one leads into a bit of interaction, so this is probably your major product of the two. But from a positional point, they're both kind of pulling in the same direction. Okay, for the second example, and here we go through and do again. Now this is an orthopara director, very strongly so. So I'm going to put a big dot here for these positions. Methyl, also orthopara director, weakly so. So I'm going to put a smaller dot. Methyl, also orthopara director, but weakly so. So we've got sort of a bit of a tie there. And finally, bromine. Also, remember, it's a deactivator, but orthopara directing, again, weakly so, so here, here, and here. So of the two positions you've got, you actually have multiple competing factors pushing for both of them, right? And this is one of those examples where there's not a clear winner. As you can see on top, you can say, for example, the bromine is trying to favor this position, while the oxygen down here is favoring this one. Both of the other two, you have a methyl and a methyl that are equally kind of split, right? They both have one methyl group kind of helping out, so we can potentially cancel that out. So really, what you're talking about in terms of a tug of war, you have oxygen as a strong donor, and you have your bromine as a slightly weaker donor. In order to break the tie, this is where you go back to that chart and see who is the stronger donor of the bunch. Given everything else being equal, I would probably put my favored position down here, where the oxygen is winning that sort of tug of war. So of those two, I'm going to put my nitro group down here, alpha to that. And really the consequence of this is we're assuming that the oxygen is going to overrule the orthopara preference of our bromine to give us this geometry here. But it is something that you're going to have to make a call based on competing factors. Okay, so I want to finish off this problem. Like we started, we said we have to alkylate, but alkylation directly is going to fail, right? If I went in with this, I'm actually going to make a product that would be a secondary carbocation, right? So it's unlikely to do a direct alkylation directly, so that's not going to work either from just an electrophile. This is an example where we're probably going to have to go in with our acid chloride to add this group and then follow that up after. So that's probably how we're going to get the carbon chain in order to get the substitution pattern we're seeing here. Again, likewise, if we already started with the nitrogen in place, we can't directly do an acid chloride addition. The nitrogen would act as our nucleophile. So we might be able to block this, right? A possibility could be to initially, let's say, start with this amide, in which case now I can at least get this reaction to work. However, this guy would be ortho-para-directing, with sterics probably being our guiding one, so this would actually give you a para-substituted one to this nitrogen. So again, not likely the right order. In the end, also, okay, well fine, maybe I'm going to start off with my nitro already in place, right? If I already have the NO2 in place, good news about the nitro is I've already got a meta-directing group, so that gives me the position that I'm looking for. However, it significantly deactivates the ring, so if I tried to just do something like iron trichloride with my acyl chloride, like this would completely shut that reaction down, right? I'm not going to be able to do this because the ring is sufficiently deactivated that we can't do alkylation or acylation, so also not an option. So we get our selectivity, we just lose our reactivity. So the path that we've got to do through this, if I start out with benzene, and this is where you can work through each permutation to kind of select what might be possible. Working through each one, you can kind of go through the different orders of addition and just work on the possible consequences. So if we were to go through and acylate it first, like this, now we have a mild deactivator, which is also meta-directing. So that's good. Now we've got that first piece in place. Now I can go through and nitrate it, like this. We have my nitro group installed, so this would be my HNO3 sulfuric acid. Now we've got the right position and reactivity matches. So now we just have to reduce it. And there's two reductions we have to do. I have to reduce this one, so that would be something like my Wolff-Kishner. This one is something like palladium on carbon, and you'd have to do both of those sequentially. Personally, I might do a first reduction where I use my zinc mercury amalgam plus acid, so my Clemmensen reduction, that's going to take care of this group. So that'll get me to my alkylated nitrobenzene, where the final step would be my hydrogen and palladium to get to me to, actually, right to the guy, like that. So the purpose of a question like this is to identify that, first of all, direct alkylation fails. That's a primary. The positional alkylation presents a consequence or a problem. You've got to get this meta group here. And then finally, the order also becomes a consequence. We have to put the acylation in first, followed by nitration. We can't do it the other way around because acylation would be not possible if the nitro was already in place.